So I'm creating a binary search tree, and this is the code, and BST interface. This is the code. Just copy over that code from textbook. Now I'm changing the unbounded linked queue to linked list from Java collections just to test this one, since I don't have that existing here. And need to create BST node. So I'm going to create BST node, new Java class BST node, and copy the code from textbook for BST node. Remove the package that we don't need. We're going to use our own package. Now we don't need this. So those rates are the errors on the side. So we use stack, and I can just use stack from the collections. So let's look at our collections. Let's see, we have stack. List queue, red list. But we have our own implementation of stack, which is done. Let's see why we want to use stack in the code first. For the size, oh, that's the iteration way. See. So just use the our linked list stack. We already have that implemented, and that should be complete. Let's check our linked list stack. Here we have pop, push, top, okay, top. Oh, we add the exceptions. So this has to do the catch when I use. So just add the exceptions. Doors and for exceptions, and this should be good, right? Still, so the method is different because I use from the collections instead of NQ and have the word NQ. I use linked list. We can do add instead. So where's the NQ, we can do just add, refactor, rename, and this is linked list instead. Since I use linked list from Java util, like only here in the code, I import this instead and change this to linked list. So let's jump to all the errors right there. Use linked list. In queue, we just do add. Oh, DQ. So we just do remove, right? Alright, so BST is done. Now let's test the code. So we don't need to import this. And binary search tree. we actually need to import from the util instead, right? The one that we just created. So import class. There you go, for the utils. Because I create a package as utils. If we go to beginning, so package utils. So util and the files itself here. Now let's see. Let's do errors. Okay, so so that's the version, the iteration version. Since it's though I have to do surrounding with my version, I have to start with try catch, right? And the throw exception, and you can just say, and for that mean queue is empty, like tree is empty. Then when you iterate for the size, it's not going to be able to do. Alrighty, so now what's the name of the test? Tree test. Yes. I need search tree test. Choose an operations. So I want to add string. Let's put name. So let's get something in the middle. Henry. Enter choice. So let's print the list. So what order you want to print? Pre-order. Let's do in order. So it should print now. Henry, right? I spelled wrong, but I mean, so enter choice again. So I'm going to add. So this is a tree now, right? So I'm going to add again. So if I add before Henry is what? George. And we can add again, add something like after Henry. Jack. Now let's print. So if I want to print in there to see the tree is working, that means it's going to match pre-order, in order, and post order. If I want to do left, root, right, we have left, root, right, which is in order, right? So that's going to be print in order is 2. So left George, right root Henry, and right is Jack. And if we want to look at pre-order, root left right, so it's going to be Henry, George, Jack, right? So let's print again and test to see if it's showing right. Pre-order, yeah, Henry. Pre-order is what? Root left right, right? Let's print. Let's try post order. Post is left, right, root, right? George, Jack, Henry, right? Let's test again. Print pre-order. Pre-order should be what? Pre is root left right, Henry first, right? There you go, Henry, George, Jack, right? So it works fine. If we want to remove, so we can test our remove now. If we want to remove the node with 2 children, then we remove Henry. When we remove Henry, Jack should replace Henry, right? So let's do that. So remove H and E1. Alright, remove Henry, returns true. Okay, good. Now let's print. So since Jack removed, if I print in pre-order, it's going to be Jack and George, right? Jack replaced Henry, right? Jack and George. So, enter 7. Stop testing. Happened at 9. Alright, so let me remove 9. Now I can print pre-order. This is George. Pre-order George Jack. Right? Yeah. So number 9 that I enter and I remove, make the order change. But we can test this works, this code. So go back to, this is just pretty much talking about how you test that. So let's look at efficiency here, and you can see this on your test. So let's revise this again together. We want to see each method, right? The efficiency of each method. Like BST, using array base and linked list base, right? Of course, array base, you know, we have to declare an array. That's going to be n. We've seen that before. Now, linked list base is 1. Is empty. Is also 1. Check 3 equals to no, right? Reset. So BST, when you reset, so let's look at the reset method on BST. For array, we just said, like the lazy approach, you just set indexed, right? For linked list, you just set it to pointer, right, to the list equals to no. But by the search tree, when we write the reset, let's look at our code here. We actually have to recursively call reset into which order, in order, pre-order, post-order. So that's why this is going to cost n, because of recursive approach. Get next returns 1. Yeah, I mean efficiency is 1. So pass order type just dequeue back. So that should be 1. And the same with the rest. Array, linked list, approach. Contains. Now, array based. If you do BST, binary search, right? I mean, if you do binary search, it's locked in, right? Array based. But linked list, when you do contains, you have to do linear search, which is n. But for BST, it's locked in, because we pretty much search on the left or right. Find's the same, like get find first. So we want to calculate the total of get. So before we get, we have to find, which is locked in. And then we process, return back, which is just 1. Then it's locked in. But for array, we already know binary search is going to be locked in. Find, return, process, same. Linked list, to find is linear as n, and process, return back 1, so n. Add. Now, when we add for BST, we always add find location to add, either left or right. So it's going to be find location is locked in. And to add, just set the link. Then that's 1, then it's locked in. For array, to find location is binary search, so it's locked in. And process to add for array, after you find location, you have to